In the previous lessons, we learned about solubility product constant where we have ionic compound dissolved in water. In this lesson, we are going to look at what happened to solubility of a substance when we dissolve not in water, but in a solution that's containing an ions, which is the same ions that's resulted from the ionic compound. When we dissolve an ionic compound, in this particular type of solution, we produce something called a common ions effect. Think of the term common ions. Well, the word common is pretty much another word for same. And it's basically the solution has the same ions as the ionic compound that's being dissolved in. Because of the common ions effects, basically it states that it would decrease the dissociation of that particular ionic compound when it is being dissolved in a solution that already includes one of the ions from the ionic compound. To understand this common ions effect, let's look at an example. We'll calculate the molar solubility for calcium fluoride when it's dissolved in a solution of 1 molar of calcium nitrate. And notice what do they have in common? Calcium and calcium. Because the solution has calcium in it already, it would affect the solubility of calcium fluoride. So let's look at this in terms of the Chatelier principle. So we have the chemical reaction CF2. If we look at this balanced chemical reaction, we notice that in the solution already have calcium. It's just like we're adding calcium to the reaction. And one way we can think how the calcium ions affect the solubility of calcium fluoride is that this calcium is pretty much being added to the chemical reaction. So if this is being added to it, guess what happened to the direction of the reaction? It's going to shift toward this way because you're adding more calcium to it. And if we shift toward this way, guess what happened? This thing will never dissolve into ions. And that would be the reason why common ions effects would decrease the dissociation of ionic compound. But now let's go back and apply the ICE table to solve for the molar solubility. Well, first thing first, we have to set the ICE table. Well, initially, we have calcium fluoride. But we know that we don't really care about the calcium fluoride because we are looking for the equilibrium constant, which we don't care about the solid. So we can cross this out. Now, what about calcium? Well, calcium before we start with 0. Well, what about the initial value for calcium? We don't have 0 because in the solution already has calcium in it already and exactly 1 point molarity. So this is expressed in terms of concentration. What about for a fluoride in this case? Well, we don't have anything. This does not include in that solution. So we have 0, just like we had before. And the change, of course, it will be plus x, and over here will be plus 2x, the same thing again. And then at equilibrium, we have 1.0 plus x, and here we have 0 plus 2x, which give us 2x as well. So this is at equilibrium. Now just plug into your KSP. So let's rewrite the equation KSP equal to, and the next thing we have to do is plug in the values at equilibrium, in this case in terms of x. So we have 1.0 plus x times 2x squared. And we can ignore that x because x is extremely small compared to 1.0. So now what we have here is 1.0 times 2x squared. And equal to your KSP for that substance calcium fluoride, 3.45 to negative 11. So we have 3.45 times 10 to the negative 11. Now let's simplify and solve for x. Well, we have 1. We can ignore that. What is 2x to the second power? That would be 4x. Now divide both sides by 4. And how do we simplify x squared to become x? Take the square root of this. So therefore, now we have square root of 3.45 times 10 to the negative 11 divided by 4. And remember, you need to use parentheses to solve this. And we plug in our calculator, what do we get? And x turned out to be 2.94 times 10 to the negative 6. So this would be the molar solubility for calcium fluoride in a solution that contains 1 molarity of calcium nitrate. And you can see that the molar solubility is extremely small. That's to the -6.